Theorem. Suppose S is a collection of vectors in a vector space V. Let's show that the span S is a subspace of V. So we need to show that the span S is non-empty. It's closed under vector addition that is defined in V and closed under scalar multiplication. So let's put a question mark here. These are the things that we're trying to prove. So first of all, remember that the span S is the collection of linear combination of these vectors. C1, V1, C2, V2, C3, V3, some dots, CK, VK, such that CIs, they are all scalars, and VIs, they belong to S, and I is bounded between 1 and K. Obviously, this set is non-empty. Why is that? Because basically it can take 0 vector. Consider V to be 0 vector. A span S cannot be empty because it includes at least the 0 vector. Now we need to show that it's closed under addition, am I right? To show that it's closed under addition and then scalar multiplication, let's take 2 vectors in span S. To show that span S is closed under addition, take these 2 random vectors like U, which is C1, V1, C2, V2, CK, VK, and another vector like V. And let's use D1, V1, D2, V2, DK, VK, DIs. They're all scalars. And then add them together. U plus V. This basically becomes C1 plus D1, V1 plus C1, C2, sorry. C2 plus D2, V2 plus the rest of them, CK plus DK, VK. Which is obviously an element in the span of S. Why is that? Because these 2 just a scalar multiplied by V1, another scalar multiplied by V2, another scalar multiplied by VK, which is basically the definition of a span of S. Now for scalar multiplication, to show that span S is closed under scalar multiplication, this is basically taking an element in the span S like U, which is C1, V1, C2, V2 plus CK, VK, and a scalar like D. Let's take D in the field F. du becomes dc1 v1 dc2 v2 plus dck vk, but basically it's just a scalar, another scalar, which is basically a linear combination of v1, v2, vk. So this is basically belongs to span S. So what is our conclusion? Our conclusion is that span S is a subspace of V.